Space agencies are now engineering permanent, self-sustaining habitats designed to support human crews on the lunar surface for years at a time. Maintaining these outposts requires a constant gigawatt-scale power supply and integrated life support systems, such as functional greenhouses. This is a significant shift from the Apollo missions. Those were limited 3-day excursions, where every necessary resource was carried from Earth in the landing module. When survival is measured in days, you can prioritize landing where it is easiest to fly. For a permanent settlement, you must land where the local geography provides the resources to stay alive. This means lunar geography now dictates the feasibility of a mission, forcing a complete evaluation of where humanity can realistically settle. Mission planners are currently navigating a trade-off between the easily accessible equatorial plains and the difficult, heavily cratered terrain of the lunar poles. We map this on 2 metrics: survival difficulty on the y-axis and accessibility, fuel costs, on the x-axis. Apollo sits in high accessibility, easy to reach but lacking survival resources. Artemis targets the opposite corner. Poles are hard to reach but vital for sustaining a base. Organizations are moving away from the proven Apollo sites because the long-term economics of in-situ resources now carry more weight than upfront fuel costs. The lunar equator is the most efficient destination in terms of physics. It requires the absolute minimum amount of rocket fuel, or delta V, to reach from Earth. Additionally, an equatorial base can maintain a constant, direct radio link with Earth for communications. The primary engineering obstacle at the equator is the lunar night, which leaves the surface in total darkness for 14 consecutive Earth days. This chart shows the resulting temperature swing. Without sunlight, the surface temperature drops to 100 Kelvin, only to spike to 390 Kelvin at solar noon. To keep a base functioning through that 2-week freeze, you have to bring massive energy storage systems from Earth. Estimates suggest it would take nearly 16 metric tons of lithium-ion batteries just to power the base's temperature control systems during the night. That mass penalty makes the equator a difficult choice for long-term stays. Every kilogram of battery capacity is a kilogram of scientific equipment you cannot launch. These illumination maps of the North and South poles reveal a different strategy. High topographical ridges at these latitudes create what are known as peaks of eternal light. Because of the moon's slight axial tilt, these specific locations at the 89th parallel receive sunlight for more than 80% of the year. This near-constant light allows a base to run on lightweight solar arrays and small battery buffers, completely avoiding the 16-ton battery requirement. However, reaching these poles requires a significant fuel mass penalty. Maneuvering into a polar orbit from Earth demands roughly 40% more fuel than an equatorial trajectory. This requirement for massive fuel loads is why heavy lift vehicles like the Space Launch System are central to the Artemis program. Agencies are essentially trading upfront fuel costs for a permanent, lightweight power advantage on the lunar surface. Comparing the 2 poles in these elevation models, the leading candidates are Whipple Crater in the north and Shackleton Crater in the south. Shackleton, on the right, is superior. It features a larger, continuously illuminated area and flatter slopes. The thermal conditions at Shackleton are also more stable, with an ambient temperature that averages 160 Kelvin year-round. One complication is that the rim of the crater does not have a direct line of sight with Earth for communications. To solve this, planners intend to use Mount Malapert as a relay site, placing a terminal there to bounce signals between the base and Earth. Shackleton's geography is also strategically valuable because of its proximity to cold traps, permanently shadowed craters holding reserves of water ice needed for life support. Ultimately, Shackleton Crater offers the specific combination of solar power, workable terrain, and water access required for a self-sustaining habitat. Despite available light, habitats cannot use exposed glass structures. To protect against solar particle events, modules must be buried under meters of lunar regolith. The physics of the lunar environment mean there is no perfect location. Every site involves a direct compromise between launch mass and long-term survival. We can simplify these choices into a decision flowchart based on mission goals. For short-duration science missions, the equator is the logical choice. Fuel savings are significant, and long-term power problems never manifest. For autonomous robotic outposts focused on power generation, the North Pole and Whipple Crater offers stable light without the shielding requirements of a human crew. But for permanent human settlement, the South Pole and Shackleton Crater are the definitive choices. Here, the higher upfront fuel cost is the necessary price for long-term survival.